In this example, we have a student in a pottery class making a flower pot in the shape of a right circular cylinder with no top. The pot is to have a volume of 1,000 cubic centimeters. The interior of the pot needs a double coat of glaze, while the exterior requires only one coat of glaze. To keep costs down, the student wants to design the pot so as to minimize the amount of glaze used. What dimensions, and dimensions here mean radius and height, will minimize the amount of glaze used? Now, we need to make a couple of assumptions here. First, we'll assume that each coat of glaze is applied with uniform thickness, and secondly, we will ignore the thickness of the pot. Now, as we read this problem and we're looking to minimize the amount of glaze, we can see that this is, in fact, an optimization problem. So, to solve optimization problems, we follow the guidelines as indicated here. And we have read the problem, we have a diagram, we have identified that our variables of interest are R and H. Now we need to identify an objective function, that is, we're going to look for the quantity that we're trying to optimize. So we're trying to minimize the amount of glaze, and the amount of glaze that will be used would be proportional to the surface area of the pot, and we're talking here, of course, about both the interior and the exterior surface area of this pot. Since the pot is cylindrical in shape, and we're looking at an open top pot, then the total surface area of this pot would be the area of the cylinder plus the area of the circular bottom. Now we also have to account here for the coating. That is, we're going to do one coat on the exterior and two coats on the interior. So, as we think about writing our objective function, we understand that it is an area function, and area of a cylinder is equal to 2 pi r h. That is, the circumference of the cylinder, of the circular part, times the height would give us the area of the cylinder. And now we need to add to that the area of the circle. The area of the circle would be pi r squared. So this part of the area function would be the exterior coating of glaze, covering the outside one coat of the circular cylindrical wall and the circular bottom. But we also now have to add to this objective function the fact that we're doing two surface areas of the interior. So to this, we're going to add the same two quantities, 2 pi rh plus pi r squared, but we're multiplying by 2 to account for the two coats. So our objective function then takes into consideration one coat of surface area for the exterior and two coats the surface area of the interior of this pot. Now we'll do some simplification. So A is going to be equal to 2 pi rh plus pi r squared. Distributing the 2 through the parentheses here, we will have 4 pi rh plus 2 pi r squared. When we combine those like terms, we'll have 6 pi rh plus 3 pi r squared. That is our area function. So we have our objective function simplified. We have our cylindrical pot. We have identified the objective function. Now we're ready to determine whether we need a constraint. And we do need a constraint because we use the constraint to reduce the number of independent variables in the objective function down to 1. Right now there are 2 variables in the objective function, r and h. So to determine the constraint, we think about the fact that the given volume for this pot is 1,000 cubic centimeters. Since the pot is cylindrical, the volume of a cylinder is pi r squared h, and that's going to be equal to 1,000. When we divide both sides by pi r squared to isolate h, we have h equals 1,000 over pi r squared. Now we're going to take that expression and we're going to go to our objective function and replace that h with 1,000 over pi r squared. And in so doing, now we'll have 6 pi r times 1,000 over pi r squared instead of the h that was there, plus 3 pi r squared. Now we'll multiply the two terms, canceling the pi, which is a common factor, and we have a factor of r common to the numerator and denominator, and that will then give us a equals 6,000 over r plus 3 pi r squared. So now our objective function, as indicated in step 4, we have used our constraint to rewrite our objective function in terms of a single variable as outlined here in step 5, and now we need to talk about the interval of interest for r, which is the feasible domain for r. Remember, r represents radius, so the interval of interest here will be from 0 to infinity. R clearly cannot be 0, but hypothetically can get as big as it wants. So now we're ready to use the methods of calculus, namely differentiation, to determine the absolute maximum or minimum value of this objective function in the interval of interest. So we're going to need a prime of r, and differentiating the a function, the derivative of 6,000 over r becomes negative 6,000 over r squared, and then the derivative of 3 pi r squared will become 6 pi r. To find a critical point, we'll be setting that first derivative function equal to 0, and now we'll solve for r. If I move the negative fraction to the other side of the equation, I get 6 pi r equals 6,000 over r squared. Now I can cross multiply the proportion and get 6 pi r cubed equals 6,000. We'll divide both sides by 6 pi and simplify to get r cubed equals 1,000 over pi. So r is equal to 10 over the cube root of pi, which is approximately 6.83, and that is our critical point. Now we need to test to determine whether this critical point is a maximum or minimum, so we'll use the second derivative test here. And obviously for the second derivative test we're going to need the second derivative, so a double prime of r, again referencing our a prime of r function. The derivative of negative 6,000 over r squared is where 12,000 over r cubed is coming from. Then we'll need the derivative of 6 pi r, and the derivative of 6 pi r is the constant 6 pi. So for that expression, when r is positive 6.83, that second derivative function is going to be greater than 0. It's going to be positive, which then leads us to the conclusion that we have a local minimum at r is equal to 6.83. And since 6.83 was the only critical point within our interval of interest, since we've proven that it's a local minimum, it is also an absolute minimum, which is what we've been looking for. So we've got r is 6.83, now we need h, and to get h we'll use our constraint, which was that h was equal to 1,000 over pi r squared. When I make my substitution for r, I end up with, surprisingly, 6.83 for h as well. So the conclusion we reach here is that the amount of glaze is minimized for a pot with both radius and height of 6.83 centimeters. What's surprising about this really isn't the numbers, it's the fact that my drawing doesn't seem to depict the reality of the numbers. So we really ought to redraw this pot. So a pot with a radius of 6.83 centimeters and a height of 6.83 centimeters looks a little more like this.